So today I'll continue speaking about the primitives. Batch draw we've already discussed, and it turns out that with this simple batch draw we can build a number of very useful features fairly easily. So that's what today's presentation is about. But before we speak about it, I want to say a few words about files component of LibGDX. Because LibGDX is a cross-platform framework, and on Android and on desktops, files are accessed in a slightly different fashion, and there is a need to kind of unify these differences in different platforms. That's why LibGDX created its own implementation of files access library, accessible through Gdx.files. LibGDX conceptualizes different file systems as areas designated for particular kinds of data. Of importance to us is the internal area. That's data files, game resources, which are packaged inside jar file. On Android platform, that's the files packaged inside .apk file. So something that is shipped and contained inside the application executable file. So that's internal area. And on top of it, we have multiple areas outside of game package file. On desktop, we have external area, which roughly refers to your home folder. We have class path area, that's where all the Java class path library files are. And there is absolute area. That's basically arbitrary spot in the file system, which you reference from the root of the file system. When you add your game resources, your sound files, your graphics files, you put them into the resources folder under source main. Under source main, you have Java folder that keeps your game source code, and you have resources folder that keeps your game resources, audio, graphics, and so on. When Gradle project is built, the content of this resources folder is simply dropped into jar file as is. So anything that you add into resources folder appears in the root of the jar file. Remember that jar file is just a zip file. And when you want to access a file that you previously placed into resources folder in your application, when it's running out of a jar file, you refer to it using internal area of your Gdx.files subsystem. So here I have sample.atlas file and sample.png files. I add them into resources folder, and they end up in the root of the jar file. So to access them in my application, I write gdx.files.internal, and in brackets, I just specify file name on its own. And that means that application will go into the root of the jar file, and it will look for these files there. If I create any subfolders underneath resources, they will become subfolders in my jar file. Remember that in its simplest form, batch draw needs a sprite batch object that provides our interface to the graphics card. And we need a texture object, a bitmap that we want to display on the screen in certain coordinates. And then we need a camera object that will project the resulting picture from three-dimensional coordinates onto our screen. Communication from CPU to the GPU takes time. And we want to minimize number of times we need to send pictures to the graphics card. So it's most efficient to package all different pictures that we use in our game project into single big bitmap picture and display only fragments of this big picture. This is the idea behind so-called TextureAltas. Based on this TextureAltas idea, we can implement a few other things. We can implement bitmap fonts, we can create animations, and then I'll say a few words about skins, which are a generalization of TextureAltas idea. Now, I've also created a lot of examples for you and I will reference them throughout my lecture today. You'll find TextureAltas example, bitmap font example, animation example, sprite example, polled input example, and input event example. So those are simple Gradle project. Download them, unzip, and open in IDEA. You should be able to compile them, modify them, and see how they work. So TextureAltas is basically a giant bitmap that contains multiple separate bitmap images somehow placed on this large bitmap. And it comes along with the atlas file that basically specify coordinates of all the different pieces and the names of all these different pieces so that we can refer to them in our program. How do we create this atlas file? LibGDX has a standalone tool for packaging pictures, but I found that using SkipComposer is by far the most user-friendly way of doing this. When you start SkipComposer, it starts with this welcome window where you can select some pre-made skin projects already. But alternatively, you can just go into File and click New. And when you do this, the project is empty. So there is absolutely nothing in it. And here under Project, we have multiple different things you can add to your project. You can create colors, you can create fonts, and you can create drawables. So if you want to build just an atlas, image atlas, you go into drawables and you add pictures. So you can add image file and, for example, you add an image here. Let's see if we can add another one. And we can add another one like this. So these are part of your skin project, but that's okay. So when you save skin project, save it somewhere in your code tree, but not inside the resources folder, because these are files which you don't use in the game directly. It's sort of source code for the skin. So what I find useful is to create a separate folder, maybe in your code tree or anywhere if you like. Well, I'll just create a folder in my desktop, skin demo, where I'm saving my skin. And it's a skin project, so I'm giving it a name, skin demo, for the lack of better word. Now to produce the actual atlas, you go into File, Export. You need to specify the folder where you put all these exported files. Okay, I'll create another folder on the desktop. I'll call it Skin Export. And you need to give your skin export a name. Skin data, which I will mention later, is saved as a single PNG file, single bitmap file, and a collection of text files. And the one that defines skin per se has extension JSON, but you can also instruct it to generate TextureAltas or font files, which are all text files, which we'll cover momentarily. So when I click export, you will see that a lot of stuff that normally present in the skin you don't have, and that's okay. And then if you go into your output, into folder that contains, oh no, that's skin demo, skin export file, you will see just a few files here. You will see a PNG file that contains 2 images that we've added. And if you had bitmap fonts or GUI elements, they would all be packaged in the same file. And you also have this atlas file that in this instance is fairly basic. And it basically says the name of the PNG file that contains the images And for each picture, it specifies the name and the position in this big giant PNG file where that constituent image is located. This is a text file, so you can edit it with any text editor. Nothing complicated here. In addition to name, each picture in the Atlas file has an index, and here it's -1, and that's okay. I'll show you where it matters. Getting back to my lecture, and that's the output. So you get just a few files exported from SkipComposer, and these are the files that you need to add to your resources folder. The rest of the Skin project is not needed for your game project. So Atlas is made of just two files, the PNG file and the sample.atlas file that references it. And inside sample.atlas, we have descriptions of different images and where they are in this sample.png. So how do we use it in the program? We need to create Atlas object, which is an instance of the class TextureAltas. And we need to create separate objects for the constituent pictures. And it has type TextureAltas.atlas region. Then in the create method, when our game starts up, we create this TextureAltas object. And as a parameter, we give it a handle to our sample.atlas file, which we take from the internal area. That's from inside the jar file. And then we use the resultant Atlas object that is created to get handles to each of the constituent pictures. And we refer to them simply by name. So hacker texture region, we obtain it by calling atlas.find region with the name hacker. And the police, we call with atlas.find region police. And after this, in the render method, we can use them just as if they were standalone textures. So we call batch.draw hacker and the coordinates where we want to draw them. And in this case, I draw 3 pictures of hacker, slightly shifted or superimposed over each other, and separately I draw the police officer. And the last thing not to forget is that in the dispose method of the game, that's called before the program terminates, we need to explicitly dispose of the Atlas object because it contains a texture. And texture is tied to resources inside GPU. So if we don't dispose it, I presume operating system won't know that the resource is released, and it might cause resource starvation subsequently. Anyway, that's how they recommend doing it in LibGDX documentation. So that's the full project with all the additional elements added. And you can find it in the project that I shared with you, which was called TextureAltas example. And if I open it in IDEA, open. So I can build it. I can create shadow jar. And when I run it from my build libs folder, I get 4 images displayed. 3 hacker images slightly shifted one over another, and the police officers on the side. There is a few other things you can do in LibGDX, in addition to just taking these images and drawing them separately. And these are bitmap fonts. If we take all letters of alphabet and render them as individual pictures, then we can draw an image of a text by drawing pictures of individual letters one beside another. And that's what bitmap font is. It's basically a specialized atlas that relates each picture to a letter. And when you can create them in a separate window in SkipComposer. So you give it a true type font, you specify name of the font you want to produce, you choose size of the letters, 16, 18, as in PowerPoint, and you need to specify the color. So do you want it to be black, red, or whatnot? And the output of it is basically a PNG with all the different letters shown. And separately, it creates an FNT file, which is a text file in a slightly different format that describes properties of this PNG and relates it to individual letters. Then in the program, you create bitmap font object, give it handle to the FNT file, not the PNG, the FNT. It's able to find PNG from the FNT file. And after this, in your render method, you just called .draw, font object .draw, you give it reference to the batch object, you specify a text you want to display and the coordinates where you want to display. Simple. So again, you have an example, and when you run it, it would look a little bit like this. I know it's very hard to see, but here on the window it says "Hello World" in really tiny letters. Now, obviously, if you want bigger letters, when you create font in SkipComposer, just give it bigger size. Okay. Now, another thing you can do with atlases is animation. Animation is basically a sequence of frames that change over time. And again, we can package all individual frames into single texture atlas. In LibGDX, all of these images have the same name, but the index parameter is used to specify number of the frame within the animation. There are separate tools that create animation atlases, where you could just add pictures in SkipComposer and then manually edit the atlas file by specifying indices in the text editor. I'll leave you to study this example. The key thing is that you need to get an array of these texture regions using find regions method of the texture atlas. And again, what you will see by running animation example.zip is a running man, and I leave you to explore it. Another thing you can do is sprite. Sprite is like a texture region, but it also contains some data. In other words, instead of specifying coordinates where you want to draw your sprite in the draw method, these coordinates, size and scale, they're already incorporated in the sprite object. So you create a sprite, you give it a reference to the texture region, and you specify its coordinates. And then you can modify coordinates using translate method. It also has rotate and scale methods in the draw. And then when you display it, you just call draw method of the sprite and give it sprite batch object as a parameter. And it already knows where it is in the world, so you don't need to explicitly specify the coordinates where you want to draw it. The reason I'm telling you about sprite is that in your game project, you might consider creating sprite-like class to represent game pieces. If you think of it, game piece is somewhere in the world, and you want to drag it, you want to rotate it, you want to flip it, and how exactly you do it is up to you, but logically, it's required. Instead of loading and creating separate texture atlases, you can create a skin, and skin has various methods which you can use. It has get region, get font, get regions. So anywhere in the preceding example where you had texture atlas, you could actually use skin object instead. And here are some points about running a SkipComposer. One thing that I haven't said before is that there is a website, ray3k.wordpress.com/artwork, where you can find a lot of pre-made skins. And with those, you download zip file, you unzip it, and you import it in your SkipComposer project. They're just like the three predefined with the SkipComposer itself, but they are external. And I think there are about 30 skins or so. Handling user input. And this is a little bit tricky. LibGDX, it's able to handle multiple kinds of input. Because on a mobile platform, there is touch, there is accelerator. On a desktop, you have mouse, you have keyboard. And LibGDX tries to provide a uniform way of receiving input from all these disparate devices. The same methods receive information about mouse clicks on the desktop and finger touches on the mobile application. Input can be handled in two ways, in a polled and event-driven fashion. With the polled input, in your render method, you check values returned by methods of Gdx.input. There is an isTouched method, which is Boolean. If mouse button is pressed, isTouched returns true. If all mouse buttons are released, it returns false. And then you can use getX and getY to get the actual location of the mouse pointer. And the same goes for key presses on the keyboard. To try it out, you can just add this simple if statement. If Gdx input is touched, print out the values returned by Gdx.input.getX and Gdx.input.getY. And in the sample project that I provided to you, it's called polled input example. The game displays single black square at the world coordinates 10 by 10, 10, 10. So the whole window is 600 by 400. And at the coordinate 10, 10, which is here, it draws a black square. So what I'm trying to do, I'm trying to click inside the black square with the mouse and see what I get from the input, and then somehow relate these coordinates to my world coordinates of the black square. I want to click on the black square with the mouse. So let's see what we receive from our program. When I click with the mouse inside this black square, I get coordinates x equal 19, y equal 380. Whereas I drawn my square at coordinate 10 by 10. Why is that? Basically, the input pointer and the world coordinates are different. The window itself, the screen coordinates, they have origin in the upper left corner. It's shown with green label, green arrows, and the green circle on this slide. So mouse pointer works in the coordinates of the window. These coordinates are integer, they're in pixels. But when we draw something on the world plane, we draw it in the world coordinates. And then we use camera object to project it onto our screen. So 10, 10 in the world coordinates actually projects into 10, 390 in screen coordinates. And that's why we have this difference. But remember that when we draw with the batch draw, it's like we are holding a camera. And if we do any more advanced manipulations with the camera, like we rotate it by 45 degrees, that black square is still 10, 10, but because my camera is tilted, when I click on this black square, my coordinates are something like 218 by 392. Go figure. How can I get 10, 10 from this 218 and 392? Not easy. And to resolve this problem, LibGDX provides interesting feature of the camera, which is called Unproject. So remember that in camera, we give world coordinates, and it somehow computes us screen coordinates. Turns out it can do the reverse operation. We can give it screen coordinates, and it returns us the world coordinates. We need to create a vector 3D object that's basically a point in three-dimensional space, to which we specify our screen coordinates. X from Gdx input get X, Y from Gdx.input get Y, and we give 0 as the z coordinate. And that's our screen point. And then we use camera.unproject. We call it on this screen point, and it returns us equivalent point in the world space. And as you can see on this slide, after unprojection, when we click with the mouse pointer on the black square, the unprojected coordinate are x21, y19, which roughly corresponds to the correct position of mouse pointer with respect to the black square in the world coordinates. Okay, and the last point I wanted to mention today is input event handling. The problem is that when we just check state of mouse in render method, when we click, render gets called 12 times while I'm holding my button pressed. And each time when it goes into the render method, it runs through this if statement and gets this print. So when I click, I don't just get one print. I get this 12 prints in a row, simply because it's printing all the time while I'm holding the mouse button. And because render is called very frequently, I get multiple hits. That's not very convenient. So the way LibGDX handles it is input events. Basically, you create a subclass of a special class called InputAdapter, which implements InputProcessor interface. And it has methods for different kinds of input events. Key down, key up, key tapped, touch down, touch up, touch dragged, mouse moved, and scrolled. For instance, when I click the mouse button, touch down method is called, and it's only called once. And it's not called again until I release the mouse button and then click it again. Input processor has all these methods, and there is InputAdapter class, which is the default implementation of input processor. So all I need to do is to subclass this InputAdapter. In the example I've shared with you, I've overridden touch down method, which receives 4 parameters: screen X coordinate, screen Y coordinate, pointer, that's how many fingers are touching the screen. If it's a mouse, it's always 0. And the button. Left button is 0, right button is 1, and the middle button is 2. And so I'm just printing out the values of all these parameters. And then I return true. When I return true, it means that event has been handled, and that's the normal way you do it when you handle the event. So with this approach, I just create an instance of this myEventHandler method and call Gdx.input setInputProcessor method. And to it, I give an instance of my event handler. That's it, that's all. And then when I click on the mouse, you'll see that touchdown event is called just once with screen coordinates, pointer, button, and I left my polled checking of Gdx input is touched just for comparison purposes. So it's with event, I get the same screen coordinates. I still need to unproject them to get screen coordinates for comparison purposes. But the advantage here is that on a single mouse click, I only get one touchdown event. So happy experimentation. Please have a look at the sample projects I've shared with you. Download them, compile them, run them, modify them, see that you understand how they work. And we'll still have to do one more section on LibGDX when we'll cover tiled maps. Thank you very much for your attention.